All right, it's a pleasure to introduce Professor Jost from MPI Leipzig, who will be talking about geometry and topology of data. Correct? Sorry if I
Yes.
confused.
Okay, thank you very much for giving me the opportunity to close off this meeting. Hopefully, it will not be a quality descent towards the end of the meeting. And in any case, even though you may be tired after a very interesting meeting, please do not hesitate to interrupt me with your questions, comments, objections, or whatever. So I'm going to speak about work that I've been doing with Pavane Yoharinath over the last couple of years, and she's actually sitting in Sun Yuk's office. So for the background, of course, you all know topological data analysis that asks when balls in a metric space intersect. And from a geometric point of view, you want to quantify that. That is, you want to ask how much balls have to be enlarged to intersect if they don't originally intersect. So topology by its very nature is qualitative, but in topological data analysis, of course, you have a quantitative dependence on radii that makes it quantitative, and that gives you all these barcodes and all the nice things that TDA offers. Whereas geometry, by its very principle, according to its very principles, is already quantitative. And as we will see, this question, how much balls have to be enlarged to intersect if they do not yet originally intersect, that can be captured and quantified by a suitable concept of curvature. And so that is the principle of our approach. And curvature, in fact, quantifies convexity. So we are in the realm of mathematics, convex analysis that offers quite powerful tools. So let me just recall some basic principles of metric geometry. So we have a metric space. And for the moment, we assume it to be continuous. So we look at continuous curves connecting 2 points. And then we look at the lengths in the standard way. We take a partition of the domain and look at the corresponding distances between the image points and sum them up. And then we make the partitions finer and finer. And then the supremum then is the length of the curve. And the space is called a length space. If for any 2 points, the distance between them is realized as the length of curves connecting them. And the length space is called geodesic if it's not just the infimum of the length, but if that infimum is also realized by one curve, which then is called the shortest geodesic. Of course, we're also interested in discrete spaces, but principles from our constructions for continuous spaces will offer us useful tools that can then be perhaps discretized or approximated. In particular, if you have 2 points, then we call another point M a midpoint between them if it sits between them, in the sense that the distance to either of them is equal to half of the distance between those 2 points, X and Y. And the metric space is called totally convex if whenever we have 2 balls of radii, such that the sum of the radii is at least equal to the distance between those 2 points, then these 2 points, these 2 balls have a non-empty intersection. And BXR always will be a closed ball with center X and radius R. So the principle is that 2 balls that can intersect, because the inequality for the radii, necessary inequality for the radii is satisfied, in fact do intersect. So that is simple and trivial principle. but our point will be to extend that or to quantify its failure when we take more than 2 balls. And just as a convention, all radii will be positive in the sequel, so that I don't have to make case distinctions. So we can express that in a more fancy way. What I've just said, take again radii whose sum is equal to the distance between the points that we want to consider. And then for every point, look at the distance from x to xi divided by ri and take the maximum over those i's that we have, just I equal to 1 and 2 here. And then we take the supremum over all radii, that is, we want to choose the radii as small as possible. So in other words, we want to find good points, x between x1 and x2, and we want to make the radii of the ball small. When x is complete, then this just comes about when we take the infimum over 2 times the distance from x to xi and divide it by the distance between x1 and x2, again takes the maximum with respect to the 2 points. And this is always at least 1, and it is 1 if and only if x lies between x1 and x2, that is, the triangle inequality becomes an equality. That is, we want to find points that sit between 2 given points, x1 and x2, and we want then to quantify to what extent that can fail. So far, everything is trivial, but the key idea now is to extend this to 3 points. So, and here comes the first definition. We call a geodesic length space a tripod space if we can realize that what I said above, not only for 2 points, but also for 3 points. More precisely, we take 3 points, x1, x2, and x3, and we seek a point that sits between any 2 of them. So for any 2 points out of x1, x2, and x3, and the point M, the triangle inequality becomes an equality. And then the point M that satisfies that if such a point exists is called a median. And we call the space a tripod space if we always can find a median. So you can, of course, reformulate the relation 3 involving all 3 points, but it's perhaps more insightful if you just draw the simple picture that I have drawn here. And here we see a tripod. You could see it as part of a metric tree. Of course, most metric spaces are not tripod spaces. So for instance, Riemannian manifolds of positive dimension do not satisfy the tripod property. But an important aspect will be then to quantify to what extent the tripod property fails. But there do exist tripod spaces, in particular metric trees, as already indicated in the picture, are tripod spaces, but also L-infinity spaces are tripod spaces. However, in those spaces in general, the median point will not be unique. I'm not requiring that the median is unique, I'm just requiring that it exists. And there's a general class of spaces that satisfy this condition, and in fact, an even stronger condition. And these are the hyperconvex spaces that I shall introduce in a moment. So, and as I already said, the strategy is to quantify the deviation from tripod property and derive a suitable abstract notion of curvature from that quantification. So once more, the tripod space. So we have 3 points, we have 3 balls, such that the sum of 2 radii always is at least equal to the distance between their centers. And then we require that these 3 balls have a triple intersection. And then, of course, we can always find the median. And so now we require that 3 balls that can intersect, because the necessary inequality for the radii is satisfied, in fact, do intersect. Now we can again reformulate that in terms of this infima. So for every point x, it takes a distance from x to xi divided by ri, takes a maximum with respect to the 3 points, x1, x2, and x3, and then find the point x that makes this as small as possible. And again, we can take the supremum over our radii. We make the radii as small as possible, and they cannot be smaller than required by the condition that Ri plus Rj always has to be equal to the distance between xi and xj for any pair of distinct points. And this condition is in fact solved. Is 3 linear equations on 3 radii, so they can be solved, and the solutions are called Gromov products. So R1 tells us to what extent the triangle inequality, if we intersperse x1 between x2 and x3, deviates from being an equality, and likewise for R2 and R3. And when we find such a point, X, or now I call it M, as this infimum is realized, then we call it a weighted circumcenter. And you can see it as a solution of an optimization problem in R3 with respect to the L infinity norm. That's why L infinity spaces, in fact, play a natural role in the theory to be developed. So now, of course, you need to ask about the existence of such weighted circumcenters. And if you have the so-called cut-zero space, I will explain that in a moment. But for the moment, let me just say that this is Alexandrov's generalization of a remaining manifold of non-positive sectional curvature. If you are in such a cut-zero space, then we get the existence and uniqueness of weighted circumcenters for triangles. So this problem can be solved under rather general circumstances. Now, we have been looking at 3 points. Now we want to look at arbitrarily many points. And there we need the fundamental definition of a hyperconvex space. Many of you will know it already, but let me nevertheless recall it. So we now take an arbitrary family of points in our space, and we take radii of balls such that the sum of 2 radii always satisfies the necessary condition to be at least as large as the distance between the centers of the corresponding balls. And then we require, when that is satisfied, that all the balls have a common intersection point. It's a strong condition. So the point is, when balls intersect pairwise, they also have a common intersection. So in the convex metric space, when this condition is satisfied for any pair of points, then those 2 balls intersect. Yeah, but we require more. We not only require that the balls intersect pairwise, so that's this simple convexity condition, we require that they all intersect, all together intersect. So there's one points that is at least one point that is contained in all of them. So again, our slogan here now is that balls that can intersect, because the necessary condition on the radii is satisfied, in fact do intersect. And of course, hyperconvex spaces are tripod spaces, because for tripod space, we require that condition only for 3 balls. Here we require it for any number of balls. Some easy examples. On the upper left, we see 3 balls in the Euclidean plane. They intersect pairwise, but they don't have a triple intersection. So the Euclidean plane is not hyperconvex. On the upper right, we see a metric tree, and there you can easily check that when any balls intersect pairwise, they also have a joint intersection, and so a metric tree is hyperconvex. On the lower left, you see L1 of the plane, and you see metric balls there. Each tilted square is a metric ball. They intersect pairwise, but they also have a triple intersection in that case. So L1 of the plane turns out to be hyperconvex, but L1 of higher dimensional Cartesian spaces no longer is hyperconvex. And on the right, finally, we have a circle which fails the hyperconvexity property in the most drastic way. If you take these 3 points there, and if you take balls of radius half of the distance between any pair of points, they're equidistant on the circle, then we have a pairwise intersection, but you have to double the radii in order to get a triple intersection. In the Euclidean plane, on the upper left, we have to extend the radii somewhat, but you don't need to double them in order to get a triple intersection. So hyperconvex spaces were already introduced a long time ago by Arnshine and Panich Bhakti in 1956. And so they showed that these spaces are complete and contractible to each of their points. There's no topology there, which is important. And they also satisfy, they can be characterized by Lipschitz extension property. If you have one Lipschitz map from a subspace of any metric space Y to such a hyperconvex space, then it can be extended to a one Lipschitz map over the entire space Y, whatever the metric space Y is. You might compare that with Kirschbaum's theorem in convex geometry. And then Isbell, and then independently Andreas Dress, found the following construction. Every metric space can be isometrically embedded in a hyperconvex space, which is called its hyperconvex hull. The hyperconvex hull of a compact space is compact, and that of a finite space is a polyhedral complex. So this hyperconvex hull is, of course, contained in the Kuratowski embedding, but in general, of course, it is much smaller and enjoys this nice property of being hyperconvex. And now let me come to the relation with topological data analysis. As you all know, in TDA, we have a metric family of points and some radius. And then we look at the intersection patterns of balls, and we add a Q simplex whenever we get a non-trivial intersection of Q plus one such balls. And then you record how the homology or perhaps the cohomology of this complex varies as a function of the radius R. I don't need to explain any further about that. So hyperconvexity here now comes in by saying that all such simplices are automatically filled whenever you have their corresponding edges. That is, whenever you have the pairwise intersections, then you also get the higher order intersections. And so all simplices are filled. And so therefore there's no local homology. Don't get any Betti numbers from these intersections. Of course, there may be global patterns. And in other words, it means that the Čech complex agrees with the Vietoris-Rips complex. Now, we can relax this definition. After all, we might be interested in discrete as opposed to continuous metric spaces. So there are two variants. On one hand, we could talk about what one might call delta hyperbolic spaces. So that means that we allow ourselves to enlarge all the radii by some fixed, perhaps small number delta in order to get the desired intersections. Or instead of an additive invariant, an additive constant, we might allow ourselves for a slight scaling factor bigger than 1, but perhaps not much bigger than 1, such that when we enlarge all the radii by that common factor lambda, then we get the desired intersections. For large radii, of course, delta becomes insignificant, and so this would be good for asymptotic considerations, while lambda hyperconvexity has a nice property that it is invariant under the scaling of the metric D. So, now, then, in particular, that also allows us to quantify to what extent space fails being hyperconvex by determining the minimal factor lambda bigger or equal to 1, that then makes space lambda hyperconvex. And then it turns out that Hilbert spaces, in particular, therefore, all the Euclidean spaces are square root of 2 hyperconvex. That is, when you have balls that intersect pairwise, then you need to enlarge the radii with most by a factor square root of 2 in order to get the common intersection. And reflexive and dual Banach spaces are 2 hyperconvex, which is about as bad as it can probably get. So some of them, of course, are better, but they're at least 2 hyperconvex. And in particular, the LP spaces are 2 hyperconvex, and if X is finite, then also lambda 1 is 2 hyperconvex, even though it's not a reflexive Banach space. But more importantly, L infinity always is 1 hyperconvex, that is hyperconvex to Kur. Now, as I already said, I wanted to relate that to curvature. So the idea is to use these concepts to compare spaces with each other or with reference spaces like the Euclidean space by looking, for instance, at this vector lambda. And of course, in geometry, such a quantification is carried by the concept of curvature, and so that naturally then leads us to an abstract concept of curvature. And so the principle is that curvature relates intersection patterns of balls to convexity properties of distance functions. That is what I want to explain now. So let's first then return to Alexandrov's cut-zero spaces. Let's take a look at the picture. On the left-hand side, we have 3 points, x1, x2, x3 in our metric space, and we connect them by shortest geodesics as indicated in this triangle, which is a little curved because the space is not a linear space. Now, we take 3 points in the Euclidean plane that have the same pairwise distances. So for example, the distance between x1 bar and the distance and x2 bar is equal to the distance between x1 and x2. And we can, of course, compare them again by shortest geodesics, which are straight lines here. And the bars in the lines indicate geodesics of equal length. Now, the space is a cut-zero space. according to Alexandrov's definition, if the distance between x3 and the midpoint of the shortest geodesic from x1 to x2 is not larger than the corresponding distance in the Euclidean plane. So the distance between x3 bar and the midpoint of the straight line from x1 bar to x2 bar. That is indicated in the picture, and that is why on the left, the curve C is curved a little inward to indicate that this distance then is shorter than in the Euclidean plane. So again, there's a definition of Alexandrov for cut-zero space, or some version of non-positive curvature. Then for our definition, then is the space has non-positive curvature if this enlargement of the balls is not larger than what you would find in Euclidean space. Or if you can find weighted circumcenters at least as easily as in Euclidean space. So just compare the two definitions of rho in a space that we want to look at and in the Euclidean space, and then we require that this infimum over all x for any triple of points in our space is not larger than the corresponding quantity in Euclidean space. So the circumcenter, the weighted circumcenter, should be at least as close to the vertices as in Euclidean space. In other words, coming back to our balls and the intersection, possibly after enlarging the balls, the principle here is that balls do not need to be enlarged more than in Euclidean space in order to get a triple intersection. As we had seen, when the balls intersect pairwise, they need not have a common intersection. You get a common intersection only if you enlarge them by a suitable factor, but in a space which has non-positive curvature, according to our definition, you need not enlarge it any more than you would have to in Euclidean space on the Euclidean plane. So again, our slogan, our balls intersect at least as easily as in Euclidean space in a space of non-positive curvature in our sense. So tripod spaces, of course, have non-positive curvature because there the enlargement factor is just 1, which is the smallest possible value. So in terms of curvature, they're the best spaces. Of course, hyperconvex spaces and also satisfy that. And then we can show that complete cut-zero spaces, that is these Alexandrov spaces, have non-positive curvature in our sense. But of course, our definition is much wider because we don't require that our spaces be geodesic or that they have unique geodesics, which are properties that hold for complete cut-zero spaces. And in particular, we can then also look at approximate versions and apply them to discrete spaces. And we can also show that a complete Riemannian manifold has non-positive curvature if it has non-positive curvature in our sense, if and only if it has non-positive sectional curvature in the Riemannian sense. There the concepts agree. So let me come to some conclusions. So the check construction in the most general version takes some cover of X, of a topological space X, and turns it into a simplicial complex with the vertex set being the index set of the cover and a simplex whenever two elements of the cover have a non-empty intersection, whenever J simplex whenever J elements of the cover have a non-empty intersection. When all intersections are contractible, so homology then equals that of X. That's the general theorem in topology. And when, of course, our topological space is a metric space, we would naturally use covers by distance balls. And then recalling that when our metric space is a hyperconvex metric space, if we use such a cover by distance balls, whenever we have pairwise intersections, we also get complete intersections. That is, when the complex, simplicial complex contains all the boundary facets of some simplex, it also contains that simplex itself. There are no holes, and therefore there are no corresponding homology groups. When we only have lambda hyperconvexity for some factor lambda that is bigger than 1, then of course non-trivial homology groups may occur. And therefore, from our perspective, hyperconvex spaces are the simplest model spaces. And then we see homology as a topological measure for the deviation from such a model. And of course, from homology groups, you extract Petty numbers as integer invariants. Now, as I have tried to argue, geometry can provide more refined real-valued invariants, and after the fundamental work of Riemann, the fundamental geometric invariants, of course, are curvatures. And in fact, the curvatures provide a complete set of invariants of a Riemannian manifold. Now, therefore, we have been looking at curvatures, and we have developed an abstract version of curvature. And in our frameworks, and the essential geometric content of curvature can be extracted for general metric spaces. And the basic class of model spaces, from our perspective now, is given by the tripod spaces, which is a special class that contains the hyperconvex spaces. And so from our perspective, the geometric content of the curvature in the abstract setting that we are developing is a deviation from the tripod condition. And Euclidean spaces then only play a subsidiary role because there's a normalization of curvature that assigns the value 0 to them. Now, we can again extend this principle for translating geometry into topology. So we take a metric space. Now we construct a simplicial complex whose vertex set is pretty big. All the pairs of points in our space and non-negative radii. And then we put in a simplex whenever the corresponding balls have a non-empty intersection. Of course, that is a gigantic space, but it is a simplicial complex now that contains all the geometric content, because as I had argued, the geometric content is contained in the intersection patterns of balls, or to what extent triangle inequalities are different from being equalities. And TDA then just means that you evaluate the topology of the slices where you keep the radii constant, where you take all the radii the same, and then vary that constant value. And so can explore then questions to develop new schemes for geometric data analysis out of that. You can look at it for a particular class of examples. For example, we can look at large networks and look at the asymptotic geometry. We are doing computational studies together with Arijit Samal in Chennai in India. And we can further investigate the geometry of hyperconvex or more generally tripod spaces. So here is a couple of references that we have been developing. In particular, we have more or less completed a monograph on these and other principles of topological and geometric data analysis. And that is submitted to a new book series, which I would like to advertise at the end. So the book series is called Mathematics of Data, and it asks for mathematical contributions at the highest level to whatever mathematical methods you can use. Could be geometry, topology, could be algebra, combinatorics, stochastics, analysis, information theory, whatever, to analyze data. And here are the editors, quite a distinguished group of people. And we invite contributions from you and from others. And this is a joint venture between our institute and Springer Nature Publishing. So with that, I can conclude my talk, and I think I've perfectly stayed to the time limit that I was given, and I'm happy to answer any questions or enter into any discussions that you might feel interesting to enter into. So thank you very much.
Let's unmute and thank Jorgen for the wonderful talk. Are there any questions or comments?
So I have a couple of questions, Jürgen. Very nice talk, thank you. They may be naive, but I'm just sort of curious about this. So, you know, curvature often is defined locally, and I think you could probably have local versions of lambda hyperconvexity and so on, which of course begs the question, you know, are there any local to global theorems? I mean, in this case, it would be something like the Hadamard-Cartan theorem.
Yeah.
Is this something that makes that is could have some substance?
Yes, let me try to answer it in the following way. Of course, originally curvature has been defined not just locally but infinitesimally from second derivative of symmetric tensor. Now, then people found that you can come up with local conditions, namely distances within triangles, that when satisfied on a Riemannian manifold are equivalent to curvature bounds. You get non-positive curvature. You can also look at curvature lesser equal than some constant. Could also look at curvature bigger equal than some constant. And such a curvature bound, and it holds uniformly across the space, is equivalent to certain convexity properties of triangles. That was result that started with Alexandrov and also Busemann. I didn't have the time to mention Busemann's work. And then Gromov, of course, pioneered all that. And so when people realized that they could characterize curvature bounds, not just in terms of infinitesimal quantities, but through local quantities, of course, then it was natural to also define space with curvature bounds in more general terms, whenever those convexity properties also made sense. So that was an important line of research. Now there's a local to global aspect. Here I've not really carefully addressed that issue because of course you can have Riemannian manifolds of non-positive curvature that are not simply connected, but whose universal cover just is simply connected. So I didn't enter into that distinction. I just required all the conditions globally, which would then combine the local or infinitesimal condition of non-positive curvature and the global condition of simple connectedness. And of course, the Hadamard-Cartan theorem, in fact, historically, this was found before Hadamard by von Mangold, actually, but that is forgotten somehow in the history of mathematics. But von Mangold was the first one to realize that non-positive or negative curvature has the effect of geodesics diverging at least as fast as in the Euclidean case. And so then the consequence is that the universal cover is of such a space is diffeomorphic to a Euclidean space, which is usually called the Hadamard-Cattan theorem. Well, both von Mangold and Hadamard realized that in dimension 2, and Cattan realized that this is the case in any dimension. And so that is a history, and that is a connection. So this global property somehow already is built into the conceptualization that I've proposed here. But of course, it remains to investigate carefully. Probably it's not very difficult to see what happens if we impose such a condition only locally. So in other words, you're pointing towards a certain gap still in what we have done so far.
Okay. My second question is curvature has been defined, I guess this, a bounded curvature, I should say, has been defined. I guess this goes back to Berezovsky. So can be defined for any metric space by considering the embeddings of quadruples of points into space forms. And so it doesn't require geodesic space at all, although it's equivalent to the usual Alexandrov curvature bounds for geodesic spaces. Have you thought about maybe some modifications of those definitions in this case?
Well, again, let me point out, first of all, historically, that goes back even earlier. So the first such definitions were proposed by Menger already around 1930. Now, however, the tripod spaces that I'm looking at cannot be isometrically embedded into any Euclidean space or into any space of bounded curvature. Naturally, from the perspective of curvature, Alexandrov type curvature, so these spaces would have curvature minus infinity.
So I mean, with a different model space.
Yeah, well, I mean, then the model spaces would be whatever tripod metric trees or L infinity spaces or so. Yeah. Now, traditionally, curvature has been defined around Euclidean space. So Euclidean space was a model, and you wanted to quantify the deviation from Euclidean space as in the positive or in the negative direction, whether triangles are more convex or less convex than in Euclidean space. Our perspective is now to quantify it from one side, from an extremum, not from the middle, but from an extremum where you traditionally would have curvature minus infinity.